Alright, so let's take a look at a field question. So we're asked, a loop of cross-sectional area 0.050 meters squared is in a changing magnetic field. At what average rate does the field need to change to induce an EMF of 1 volt between the loop ends? Okay, so we know for our answer, this is another calculation question, so we know that EMF needs to be 1 volt. We know the area of the loop. So area is 5 times 10 to the minus 2, and this is in meters squared. So the formula we're going to use is EMF is minus N times del flux del T. We need to solve this for del flux del T. So divide both sides by minus N. This gives us del flux del time is equal to minus EMF on N, and this is going to be equal to minus 1. We know that N is 1. This is a simplifying assumption because there's just a single loop. So we've been told a loop of cross-sectional area. We're going to assume that's a single loop. So now we have the seemingly not hugely helpful identity that del flux del time is equal to minus 1. Well, we can actually use this to find out how the field has to change. Because we know the change in flux is only going to be a consequence of the magnetic field, right? We're assuming, we are making an assumption at this point. We are assuming that the loop stays perpendicular. Assuming loop stays perpendicular to the field. So this means change in flux is going to be the area of the loop times the field at time 1 minus area of the loop times the field at time 2 divided by the change in time. And this is going to be equal to minus 1. Now we've got an A in common in both terms up the top, so we can divide both sides by the area, and we will find that change in field, because we've got B1 minus B2, in this case that's going to be change in field, over change in time, ends up being equal to minus 1 over the area. Well, the area was 5 times 10 to the minus 2, so this is minus 1 over 5 times 10 to the minus 2. And this is actually the answer that we want, right? Because we were asked to find what average rate does the field need to change. That's del B del T, right? Not flux, but the field. And so this means that del B del T, it's really weird doing this without calculus, incidentally. The algebra-based physics course has a whole bunch of weird quirks, and one of them is that when you're trying to find rates of change, you can't just find functions and differentiate or integrate them. You just have to deal with them algebraically. So we have some very unusual sort of algebraic working in here, but it does make sense. So del B del T, it essentially makes sense. So del B del T ends up being minus 20, and this is Teslas per second. So this is going to be the rate of change of the field. And this is the answer to this question.